In this video, we are going to take the 5 elements that we saw in the previous video and use them to create a template that describes all control tasks. That template is known as the Markov decision process. But what exactly is a Markov decision process? Well, it's a discrete time, stochastic control process. It is a control process because it's based on decision making to achieve the goals of the task. It is a stochastic process because the agent's actions affect only partially the evolution of the task. And finally, it's a discrete time process because in the tasks that we are going to represent with this template, time progresses in finite intervals. That is, t equals 1, t equals 2, and so on. Here's a diagram representing the Markov decision process. In this process, the agent interacts with the environment. At the start of the task, the agent observes the initial state of the task, and based on it, it takes an action. This action produces an effect on the environment which modifies its state. As a result, the agent observes again the new state in which the task finds itself and receives a reward from the environment which gives feedback on the effect that the previous action had on the environment. Then, based on the new state, the agent takes another action, and the cycle repeats itself until the task ends, either because the agent has achieved the goal of the task or because it has failed for some reason. As you can see, this model, called the Markov decision process, represents in an abstract way the behavior of every control task that we are going to face and allows us to work using the same template with all of them. Thanks to the Markov decision process, we can analyze very different tasks using the same concepts. An additional advantage is that we can describe a control task in a very simple way, based on 4 objects. The first object is the state space, which consists of all the possible states in which the task can find itself. The second is the action space, which consists of the set of all the actions that the agent can execute in the environment. The third object is the set of all rewards obtained by performing each action in each state. And the last object is the set of probabilities of changing from one state to another by taking an action. If we know these 4 elements, we can perfectly describe a control task. And we can use the same structure to analyze different tasks simply by modifying the content of each of these elements. To give an example, in the game of chess, the state space consists of all the valid configurations of the board and all the possible values for the remaining time. The action space consists of all the valid moves in each state of the board. The set of rewards consists of the rewards obtained by taking each action in a valid state. And finally, the set of transitions consists of the probabilities of reaching each successor state by moving a piece. These Markov decision processes have an important property, and that property is that the next state visited depends only on the current state, and not on the previous ones. That is, the process that we have followed to reach the current state does not influence the future states that we will see. That is exactly what this expression here is trying to tell us. The process has no memory. If a process satisfies this characteristic, it's known as a Markov process. In fact, the Markov decision process is an extension of a process known as a Markov chain. In this chain, the process starts in a particular state, S0, and at each moment in time, it has a probability of changing states to S1. and that probability is 70%. And also with 30% probability, it will remain in state S0. The Markov decision process is a similar kind of process that incorporates actions and rewards. In this example, the process starts in the state S0, and the agent must take an action, either A0 or A1, and based on a set of probabilities can either change its state to S1 or remain in S0. Now that we understand the control tasks in an abstract way, thanks to the Markov decision process, we can now work with all of them with a single template and develop solutions common to all of them.